So I'm Janelle. I've been working a lot with Nick on some of this Aeolus stuff. So today we're going to look at some of the modeling of spatial temporal grain size effects on coastal Aeolian sediment transport. So starting out, we know that dunes and beaches and just coastal environments in general are kind of built up by a combination of both hydrodynamic and Aeolian sediment transport processes, where the wind-blown or Aeolian sediment transport plays a pretty important role in development of dunes. It also can contribute to sediment flux into inlets and other shallow water bodies. And traditionally, there haven't been a lot of tools that are available in order for us to kind of look at this complex system and consider both the hydrodynamic and the Aeolian processes. So starting out with just a little bit about Aeolus. Aeolus is an Aeolian or wind-blown sediment transport model. It was specifically designed for supply-limited systems, so it works well in coastal environments. It's able to incorporate a bunch of different processes. So we have vegetation. It can handle multi-fraction sediment transport, surface moisture, and some others as well. And so what we're starting to do is couple Aeolus with the Coastal Modeling System, or CMS modeling suite, so that we're able to incorporate both flow waves, the subaqueous sediment transport with the subaerial sediment transport to look at a more holistic morphology change for both the near shore and also in the dunes, and kind of incorporate the different parameters from both models and what both are able to handle. So previously, we've done a little bit of work with 1D Aeolus, specifically looking at some of the multi-fraction capabilities in 1D. So we started out kind of doing some of the annual sediment fluxes on the beach using Aeolus and the SandSnap database. We gave a tech discussion on that last year, 2 years ago. But we can also see that we can, Aeolus over here on the right-hand side, you can see that it's able to kind of incorporate some of these changes in the sediment fractions that we're seeing on the beach, as well as different morphologic changes over time as well. And some of our academic partners at TU Delft and Lund University and Deltares have done some more academic cases with Aeolus. Let's see if I can get this to play. Looking at bark and dune development, as well as some parabolic dunes. So there's a lot of cool stuff that has been going on with Aeolus recently, and has a pretty active development going on. So some of the more recent code developments Aeolus have focused on some of the 2D capabilities of the model, so adding in new numeric solvers, wind routines, threshold formulations, some surface moisture as well. And so we had previously tested these 1D multi-fraction Aeolus capabilities, and so now we're kind of expanding that to test some of the 2D Aeolus capabilities. And while we were doing this, finding and debugging some of the problems that we were having in the 2D model, which is important so that we're able to couple this model with other 2D hydrodynamic sediment transport models such as CMS. So we want to make sure that we're getting reasonable results in the Aeolian regime before we start to move and couple it with hydrodynamic models as well. So here we're just kind of trying to test the limits of the 2D capabilities for Aeolus, specifically looking at the multi-fraction sediment transport and then also some of the morphology change processes as a part of this 2D Aeolus CMS coupling. So our primary research question that I'm going to be talking about today is, do spatial and temporal variations in sediment characteristics influence the alongshore variations in dune growth? So I'm going to start out with just a little bit of an overview of multi-fraction sediment transport in general, and then look at two different 2D demonstrations with Aeolus. The first focusing on the individual composition of the core slag deposits and that influence on alongshore sediment transport or sediment dune fluxes into the dunes. And then also looking at then the long-term influence of these grain size variations. So starting out, kind of giving a little bit of an overview of why this might be important. At the field research facility, we do collect about semi-weekly subaerial sediment collections in front of our dune LiDAR. We have about 10 points that we collect. And so we can see over here on this right-hand P color plot, we started this in about October of 2019 and has been continued about weekly since then, with a few gaps from COVID and other things. And so you can see here that, you know, our grain size is varying a decent amount in both space and time, with right now the largest D50 grain size on this color bar as 0.6 millimeters, but we've seen the D50 range all the way up to over 1 millimeter. And it is pretty variable throughout the space and time. And then we also have been collecting about monthly subaqueous collections from the LARC, also following along a transect in front of the dune LiDAR, but that data is not being considered here. It's just another piece of data that we have started collecting. So these coarse grain sediments that we were seeing in that P color plot before are showing up kind of as this orange hue. So these are like coarse slags, they're kind of shell, some gravelly material. And this, you know, the fact that it's showing up as like an orange color can be leveraged for different remote sensing capabilities, particularly because we do have these orange hues that are showing up in our Argus images as well. So they're a little bit more challenging to see in the Argus images, but we can kind of see, if you can see my cursor here, we have a few, and up in here. So we've been working with Evan Goldstein at UNC in Greensboro on this machine learning algorithm that he has to kind of pull out where these core slag deposits are located from these Argus images using the characteristic orange hue that they have. And so from this information, we can kind of start to get like a time stack of what our bed composition at the FRF looks like over time. And so, you know, looking at these 6 days from 2018, we can see that the bed composition at the FRF is pretty variable in both space and time. And so this can kind of help us to look at, you know, what are some of these implications that these coarse slag deposits and coarse grain sediment has on our sediment flux into dunes. And so part of that is important because when we have these coarse slag deposits present on the beach, they do tend to reduce the amount of sediment that's available for Aeolian sediment transport, which then can limit the volume flux of sediment into the dunes. And so how this kind of is working is when we have a wind speed that's able to just pick up the smallest fines that we have on the beach, but not able to get at the medium or the more coarse grain sediments, we can see that we're left with the beach that only has these coarse grain sediments, and therefore we don't have sediment that's available to be transported. And so this can really be remedied by having, you know, if there are some medium grain sands present and you have a higher wind speed come through, that can pick up the mediums, but then you're still left with the really coarse material. And then we have hydraulic mixing from waves and tides that can kind of mix up the sediment and can reintroduce some of these fine sediments into our system again to be available for Aeolian transport. So just to iterate again, Aeolus is a process-based Aeolian sediment transport developed for supply-limited systems such as coastal environments. It can simulate spatially variable multi-fraction sediment transport, and it is able to simulate the sediment sorting and the bed armoring processes that I had just talked about in the last slide. So it does make it pretty well suited for coastal environments and recent developments are including surface moisture and surface roughness changes, as well as vegetation capabilities. So looking at these two 2D applications, starting off with this main question of, does cross-shore and alongshore variability in grain size drive alongshore variability in dune growth? And so kind of splitting this into two parts. The first is investigating the influence of the coarse lag deposit composition on alongshore sediment supply to the dunes. This is what I had done for coastal sediments and presented in a poster there. And then also looking at the long-term impact of variations in cross-shore and alongshore variations in dune size, in grain size on dune growth. So looking at, over a long term, how do these coarse lag deposits and coarse material impact dune growth? So both kind of questions and topics started out pretty similarly. We utilized the Argus images to create a rectified bed composition that we can see here, where the dark purple is the vegetation, the blue is just our regular sand, the more green is our coarse, and the yellow is water. And it kind of is this upper region in here from our Argus image. And with this, we have the 3-meter contour elevation labeled. This is what we had considered to be our dune toe. And so when we're calculating volume fluxes, we're calculating them across the 3-meter dune toe. So these rectified bed compositions were then converted into external Aeolus mass files to kind of create this overall bed composition variation in the grain size for Aeolus. So then to get the grain size that would be used for both the regular sand and the coarse sediment, I separated the subaerial grain size data that we had collected in front of the dune LiDAR from October 2019 to March 2022 into a regular sand and a coarse sediment distribution, which can be seen here over on the right. We had the regular sand with a D50 of 0.32 millimeters, and the coarse sediment came out to a D50 of 0.53 millimeters. But we can kind of see from this box and whisker plot that the D50s for the more coarse sediment does vary a large amount. So we had D50s that were 1.1 millimeters, and we've had a couple of other ones since March of 2022 that are also in this 1 millimeter grain size range. And then here is just another representation of our P-color plot, similar to the one shown earlier, but now just limited to October 2019 to March 2022. So using this grain size, these two separate grain size distributions, the bed composition that we had gotten from the Argus images, and then also using our dune LiDAR data that we had collected to get a beach morphology, and then also looking at wind and waves and tides that are also collected at the IFRF, using all of this information to then put into Aeolus to look at these, the impact of the coarse sediment and multi-fraction sediment transport in coastal environments, specifically at the IFRF. So starting first with looking at the influence of the individual coarse lag deposit compositions on the alongshore sediment supply to dunes. This is done by running Aeolus with a fixed and constant cross-shore wind speed ranging from 5 meters per second to 20 meters per second. So we did a 5, 10, 15, and 20. Each simulation was run for 7 days, and then all of the different cases used the measured regular grain size distribution that I had shown earlier. So it had the D50 of 0.32 millimeters. And then for the coarse cases, we used we used the original measured distribution that was also previously shown, and then created 20 hypothetical grain size distributions. So the first one was created 10 that varied the standard deviation, effectively changing the sorting of the grain size distribution. And so that can be seen up here on the top right in the purple. So we can see changing the standard deviation is increasing or is changing the sorting of the distribution and allowing for, a really narrow distribution to a wide distribution. And then we also created 10 that had a varying D50, so kept the overall shape of the distribution the same, but simply shifted it to include so that we were effectively increasing just the D50 and also the distribution to include just larger grain sizes, and that can be seen down here in the bottom right. And so this one ranged from a D50 of 0.35 millimeters, so really close to the fine sand, all the way up to 0.8 millimeters. So starting to look at some of the results when we're looking at the two original grain size distributions for the coarse and the regular sand, we can see that there is a fair amount of alongshore variability in the sediment fluxes to the dunes. And we can kind of see when you look at these higher wind speeds, even starting out at the 10 meter per second wind, that these dips in sediment flux kind of correspond to where we're seeing these coarse lag deposits. And so that's kind of interesting. And there's tends to be a little bit less variability with the smaller wind speeds, which does have a reasonable effect, as you would think. The smaller wind speeds are not able to mobilize a majority of that sediment, so the coarse sediment isn't really having much of an impact because even the fine sediment can be hard, is rarely moved by a 5 meter per second wind. So then going to look at the two different hypothetical scenarios that we had created. So starting out with increasing the grain size, so up on, or over on the left, looking at increasing the overall grain size of the distribution, we can see that the higher wind speeds are actually more affected by increasing the overall grain speed or grain size. A lot of this is again due to the smaller wind speeds aren't able to mobilize as much of even the regular sediment as the higher grains or higher wind speeds are. And as we're increasing that overall grain size, you can see that it's kind of increasing the range between the minimum and the maximum calculated alongshore volume flux. So we did this, the volume fluxes were calculated along the 3 meter dune toe, and then we found the minimum and the maximum, as well as the mean volume flux that was along that 3 meter contour elevation. And so when we're looking at these higher wind speeds where we're seeing a higher range in the minimum and the maximum, the coarse deposits are starting to have a little bit more of an impact with the higher wind speeds. And you see that with the 10 meter as well, just seems to level out a little bit sooner in the overall grain size. And then when we start to look at the standard deviation of the coarse lag deposits, so the sorting of them, we get a little bit of an opposite effect where the smaller wind speeds are more impacted by the changing standard deviation than the high wind speeds. And again, this is kind of related to the overall composition, but as we're, increasing the standard deviation, we're allowing for a wider sediment distribution. So we're including some more of those fine grained sediments that when we have the narrow distributions are not being included. And so the wind is able to mobilize some of those smaller distributions that are now present in that composition. So it was kind of interesting to see that the spatial and temporal variability in the grain size does have an effect on the magnitude and alongshore variability of the dune growth rates when you're looking at these like constant wind speeds in the cross-shore direction. So moving on to our longer term impact of the variation of cross-shore and alongshore sediment grain size on dune growth. So this was similar. So we utilized the Argus images and the dune LiDAR from now 2016 through 2020. And we did this to obtain a daily bed composition and elevation. And so with this, we updated the morphology and bed composition at the start of each day. And we chose to do this because we weren't primarily focused on the accuracy of the morphology change. We were more looking at the volume flux and how that can impact the, or looking at the bed composition and how that will impact just volume flux to the dune. And so you can see here, looking at a snapshot of one of these days from 2019, that the volume flux, though relatively small, there is variation in the alongshore. This is a fairly complex bed composition day, but we can see that there are some variations in the volume flux. And so when we look at 2 days together, so September 16th, 2019 and September 17th of 2019, we can see that both days do have a good amount of variation in the volume flux, but they're different, and we see corresponding differences in the bed composition on the 17th from the 16th, as well as morphology change for both days, though relatively small changes, but each volume flux in the alongshore is different for each day. And so as we start to look at some of the longer term results, so looking at all of our volume fluxes across the dune toe, and kind of try to piece together what environmental factors can be driving some of these changes in our volume fluxes and alongshore variations in our volume fluxes. We can kind of see that there's not a really easily distinguishable trend. We can see the wind speed does seem to have the most concise sort of a relationship between the mean volume flux. But then when we're looking at, how much coarse material or regular sand is on the beach, as well as the total water level, wave height, beach width, and the wind direction, we're not seeing a super easily definable trend, which kind of leads us to believe that there's multiple things influencing what is causing these variations in alongshore dune growth. And so if we pull out even just two, or try to add in a few more, looking at the relationship between multiple, so looking at wind speed and the beach width, or the cross-shore wind speed and the wave height, we again can see that there's not a super concise trend, but that there is, some information that we're getting told, and again, it's just leading towards, we aren't seeing one thing that is contributing individually to these variations in volume flux. It is kind of a compilation of multiple things together. So kind of in summary, we were looking at, the cross-shore and alongshore variations in grain size and the influence that they have on variations in dune growths in the alongshore. And so we can see that these cross-shore and alongshore variations in grain size can contribute to the variations in alongshore dune growth, but grain size is probably not the only factor affecting these alongshore growth variations on a longer time scale, and a lot of that can be related to if you have a really significant wind event coming through, and you have primarily fines on the beach that day, that can be driving some of this, can be driving a lot of volume flux into the dunes that day, or if you had more coarse material present on a day where you have a high volume flux, it can kind of overburden kind of the smaller, more average wind events that are also bringing sediment flux into the dunes. And so with this, we've kind of led into a cycle of some of the model testing and bug fixing, and we've updated the code on the Aeolus GitHub. We've created a bunch of case studies and set up codes for 2D multi-fraction sediment transport. And then we've also started working on the CMS Aeolus coupling for some more complex cases and trying to narrow that down as well. Thank you. I can take any questions.